Hello everyone and welcome back to A&P. What we're going to do for today is talk about transmembrane potential and action potentials on here. Some of these slides have already been highlighted from a previous lecture, and I'm just going to sort of discuss why those highlights are there, but I'll be putting my little markers and things on stuff that are it's really important. I also had planned on having all of your lab practicals graded. Not there yet, so I'll get them all graded and posted by this afternoon at some point, and as soon as I get them done, I will email you guys, so I'll let you guys know that they're all done. But as of this moment, about halfway through, and I'll get the other half done sometime today. All right, so without further ado, let's go ahead and get started. So where we last left off is that we were taking a tour of a neuron, and we talked about, the different parts of it with the dendrites and how they are the receiving end. We also talked about how the axon is the sending end, so the dendrites receive the message, the axons are going to send it off. The axons will send the message off. We also talked about how we have these mesel bodies, which are just collections of rough endoplasmic reticulum and ribosomes, and their whole job is to make these neurotransmitters, which are the vehicle through which the message is sent, and when we're talking nervous system. We even talked about the different types of axons that we can find. We talked about the different sorts of structures that you'd find in a nerve cell. You had the axoplasma, which is the plasma membrane, in the the cytoplasm in the axon, and we talked about how the axon lemma is just the plasma membrane of the axon. We've even talked about how we have neurofibrils and neurotubules, and they help to carry things from one end of the cell to the next end of the cell. So there's been a lot of discussion that we've had so far just talking about what a nerve is and the job of the neuroglia, that they are the supporting cast members, and the nerves are the one that send and receive the messages. So on our previous lecture, it was really just kind of a tour of a nerve cell. Today we're going to get it to work. We're going to talk about how an action potential is generated, and you already have a little bit of an understanding of that, and you probably remember from the muscle chapter that it's got something to do with acetylcholine as well as with sodium ions, and we've already talked about how we'll go from a negative number to a positive number in an action potential. So what we're looking at now is just kind of a roadmap of where we're going to go. The first thing that we're going to discuss is what we call resting potential. And resting potential, something that you're already very familiar with, is at negative 70 millivolts. So resting potential, there can be a change. So this neuron receives a message, there's a change, and it's going to generate a graded potential. Now the graded potential here is just us getting a little bit away from negative 70 millivolts. So sometimes just getting to negative 65 or negative 60 is enough to give us a localized change in membrane potential. So that's what a graded potential is. And notice where this graded potential is found. It's found at the very beginning of the axon, and we call this the axon hillock. And this graded potential may or may not produce an action potential. If it does produce an action potential, that happens along the length of the axon, and that's going to trigger the synaptic activity. So the neurotransmitters being released, or the neurotransmitters not being released. It depends on what kind of neurotransmitters we're talking about, what kind of message is being sent. And then the receiving end of it, the postsynaptic cell will process that information. So everything on this roadmap are going to be topics that we discuss in detail as to how do we maintain resting potential, how do we generate a graded potential onto an action potential, and what the synaptic activity is at the end of the terminal, and then also how the cell that's receiving the message processes that information. So in order to maintain or to have a transmembrane potential, there are three things that we require. The first thing that we require is extremely important, and it's going to be the concentration gradient of these two ions, sodium and potassium. Sodium and potassium ions, there should be different concentrations of them both inside the cell and outside of the cell. Maintaining those different concentrations in and out of the cell helps to make sure that we stay at a resting potential of negative 70 millivolts. We also have to have selectively permeable channels through which sodium and potassium are able to go through. So in order for us to maintain that, once again, the concentration of sodium and potassium both in and out of the cell needs to be maintained. And that's done through the selectively permeable channels. And when we do that, we're able to maintain our resting potential at negative 70 millivolts. So there are a couple of different types of forces that act across the membrane that allow for us to maintain this resting potential. You have passive forces and you have active forces. So with passive forces here, remember they're not actually using any energy. It's kind of just as the law of physics or the law of thermodynamics, the law of osmosis and diffusion. This is just how it happens. So we have two gradients that are established. Keep in mind, when we talked back here about sodium and potassium, we understand that sodium and potassium are both chemicals. They're both chemicals that are found on the periodic table. They're elements. However, they have a positive charge. So it's not just the elemental form of sodium or potassium. This is the charged aspect of it. So if it has a positive charge, that means it gave away an electron. And because it gave away an electron and it's positively charged, it has an electrical aspect to it as well. So the passive force that helps to maintain that transmembrane potential are the chemical gradients, where just the chemical concentrations of these chemicals, sodium and potassium, and because they have a charge to them, they're both positively charged, we also have an electrical gradient. So the electrical gradients will separate the positive and the negative ions. So as a result, we have a potential difference. So as you can probably already surmise from what we talked about in the muscle chapter and when we talked about what resting potential is, a cell that is at rest is more negative on the inside than it is on the outside. The reason it's so negative on the inside is because you have a lot of these proteins, and a lot of the way that these proteins fold is that they are, if you had to measure the charge to them, they would be negatively charged proteins. So the electrical and chemical gradients still both relate to sodium and potassium ions, but then there are also other ions and other charged particles that help to maintain the inside of the cell at -70. Big take-home message from all of this is that a cell that is at rest is at -70 millivolts. So once again, here we're looking at an electrode, and it's going through the plasma membrane. This cell is not doing any work, and we notice that the inside of the cell is negative, and you notice you have all of these giant negative proteins on the inside of it, so that helps to, it's one reason why the cell is negative. And then we also have these passive channels of a potassium channel, and then you have a sodium channel. So with the potassium channel, notice that the potassium ions, which are going to be the orange balls, they can just passively leave out whenever they want to. If we look at the chemical concentration gradient, there are more of these orange balls on the inside of the cell than there are on the outside of the cell. So as a result of diffusion, they're going to want to go out. So the potassium ions are going to want to go out from an area of high concentration to an area of lower concentration. Conversely, if we look at the sodium ions, the purple balls, they're much more numerous on the outside of the cell. Lots of sodium ions on the outside. And once again, as a result of diffusion, they're going to want to come back in. However, we don't have a channel for them to leak back into. We only have a channel for them to leak out of. So they're only going to leak out. And the way that they have to come in is that a neurotransmitter will help to bring them in. But that's another end of the story. But so for right now, understand the inside of the plasma membrane is more negative than the outside of it, and that you have these potassium channels that will leak out passively potassium ions, and you have sodium channels that will leak out sodium ions passively. And whenever we use the term passively, that means that it's not going to require any energy, which is different from what we see here, the sodium-potassium exchange pump. Notice that we have potassium ions and we have sodium ions. We have for every 3 potassium ions that go out, we have 2 sodium ions, every 3 sodium ions that we go out, we have 2 potassium ions that come in. And the big difference between these leak channels and this pump is the use of energy. So this would be considered an active force that helps to maintain the resting potential. So all these potassium ions want to leave. They want to go from an area of high concentration, lots of them hanging out on the inside of the cell, to an area of lower concentration, not so many hanging out here. However, we need to have some of these positively charged entities in here, or this -70 number would be way, way, way negative, like negative a billion. So we have to have some positively charged ions coming in. So the sodium-potassium pump will bring in 2 potassium for every 3 sodium that it pumps out. And we'll talk more about the sodium-potassium pump and its role in maintaining resting membrane potential. So the electrical current and resistance, the electrical current is a movement of charges to eliminate potential differences here. What we consider resistance is the amount of current a membrane resists. Now this is very important when we start to talk about myelination, so that's why I put an M there, because the resistance that is established by the myelination, either from oligodendrocytes in the central nervous system or from Schwann cells in the peripheral nervous system, is important because it allows the electrical signal to jump from one node to the next. And we talked about that a little bit at the very tail end of our last discussion. So with resistance here, the more resistance you have, the less current is going to be able to go through there. Myelination creates this resistance. So in spots where the axons are myelinated, the current can't just go straight through. It has to jump from one spot of non-myelination, or what we call a node, to another spot of non-myelination, or node. So together with the electrical gradient and the chemical gradients that we have for any particular ion, it's just going to be the sum of the chemical and electrical forces, which we've kind of already talked about because sodium and potassium are both chemicals, and at the same time, because they have given away an electron, they are also ions and they have an electrical charge to them. So the electrochemical gradient that acts on these ions that pass across the plasma membrane give us a type of potential energy. This slide here is really just more of a textual discussion of what we're looking at on this slide. So the electrochemical gradient for potassium, as we've already established and we saw in the previous two slides, that at normal resting potential, we have more potassium ions inside than we have outside. So those potassium ions are going to want to leak out. We still have some potassium ions that are coming in, so the chemical gradient, the chemical is leaking out. We bring in enough of them to make a change in charge. Remember that sodium-potassium pump that we brought some of those back in so that our negative number isn't super, super, super negative, but the overall net movement, the chemical aspect of the way potassium is moving, combined with the electrical aspect of the way the potassium is moving. Chemical, they're just leaking out. That chemical wants to move from an area of high concentration to low concentration. Electrical, the sodium-potassium pump wants to bring in just a couple of those sodium ions so that we can have some charge here so it's not super, 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 super negative. But overall, there are more potassium that are leaving that are coming in. So the net electrochemical gradient is that the potassium moving out. So if we combine both of those together, the net electrical chemical gradient tends to force potassium ions out of the cell. And when that happens, that's why we're able to stay at negative 70 millivolts. We understand exactly what it is that keeps potassium moving out, so it's potassium leak channels. So this is all kind of, it may seem kind of complicated, and it seems like we're having a lot of discussion about just potassium and just sodium ions, but it's vitally important that we understand this. In order to stay at negative 70 millivolts, we can't just say, oh, I'm going to be at negative 70. There are chemical and electrical forces that allow for this to take place. Those passive forces, those leak channels, well, that's just the way diffusion works, something you learned long, long ago about molecules moving from an area of high concentration to low concentration. So we see that happening with the chemical aspect of potassium. Now, the sodium-potassium pump, which is denoted by this white arrow, we have to bring some of those positively charged ions in, because if we don't, this number will be so negative that would be really difficult to generate an action potential. So we have to have some of them coming in. However, for potassium, we haven't even started to talk about sodium yet. For potassium, there are overall more potassium ions that are leaving out of the cell than there are coming in. And that's why, and that's one of the reasons that we're able to stay at negative 70 millivolts. If, however, we had the chemical gradient match the electrical gradient, where the amount of potassium ions that were leaving was equal to the amount of potassium ions that were coming in for the electrical forces on there, then if this were to continue to reach equilibrium, we get down to negative 90 millivolts. So if the membrane was able to freely, was permeable to potassium ions, the outflow of potassium would continue until the equilibrium was reached. So if the amount going out and the amount coming in became equal, we'd be at negative 90 millivolts. And there are some points in time when this happens for potassium, and we need that to happen, and we call that hyperpolarization. So in hyperpolarization, we want to have the sort of equilibrium established because eventually we can get back up to negative 70 millivolts. But if this were the case all the time, it would be extremely difficult to generate another action potential if this number just got too negative. So when we look at sodium ions at normal resting membrane potential, the chemical and electro gradients combine to drive sodium ions into the cell. Notice we have more sodium ions on the outside than we have on the inside. So because of the chemical aspect of sodium and the laws of diffusion, sodium wants to move from an area of high concentration to low concentration and wants to come back in. The electrical aspect of it, because once again, we're more negative on the inside than the outside, is that we still want to bring sodium ions back in. So the overall electrical chemical gradient itself is that sodium ions want to move into the cell, or the overall movement of them is into the cell. Now, if we have sodium and the chemical gradient and the electrical gradient with it's moving sodium in and out of the cell, if the plasma membrane were freely permeable to sodium, the amount of sodium would continue until once again equilibrium was reached. The chemical and electrical gradients would be equal and in opposite directions. So we wouldn't have any net movement of sodium, but look what happens to our charge. It goes up to plus 66. Whereas on this previous screen here, if we have the potassium ions, the amount leaving that was coming in, we'd be hyperpolarized. If the amount of sodium ions that were coming in were equal, then we would be well beyond an action potential here. So it's not just one of those ions alone that's able to maintain our resting potential, it's both of them working together. So the active force that works across the membrane, remember if it's an active force, it's going to have to use some sort of energy. The passive forces were those leak channels, sodium and potassium leak channels. The active force here is the sodium-potassium exchange pump, or sodium-potassium pump. If it's an active force, it has to use energy. So it takes out every 3 potassium ions and brings in I just keep saying that backwards, every 3 sodium ions, it brings in 2 potassium ions. By being able to do this, it will balance the passive forces. So the forces that we talked about on these slides here, it's able to balance them by taking out 3 sodium and bringing in 2 potassium. And the working of the sodium-potassium pumps help to maintain us at our resting potential of negative 70 millivolts. Right now, this all might just seem like a lot of talk and like, okay, what's the point? But as we get more into generating an action potential and a graded potential and all that stuff, it will all make a lot more sense. So it's just kind of giving us a background information so that we can be prepared to understand the inner workings of action potentials. Sodium-potassium channels, sodium membrane permeability to sodium-potassium determines transmembrane potential, and these things we've all kind of talked about. Channels can be either passive or active. Passive channels are also called leak channels. These passive channels are always going to be open. They never close. There's nothing to close in there. So if potassium wants to go out, it can freely go out of this channel. If sodium wants to go out, it can freely go out of this channel, and so forth. Active channels are also called gated channels. They're not always open, so they're going to be open and closed in response to some sort of stimuli. So when we're at resting potential at negative 70 millivolts, most of these gated channels are closed. Opening of these gated channels are usually, if we're generating an action potential, they're usually sodium gated channels that will open up as a result of some sort of change in transmembrane potential, and it will allow sodium ions to come into the cell. Because if you'll remember, back here, there's more sodium on the outside of the cell than there is on the inside. So this membrane is not permeable, freely permeable to sodium ions. They just can't come across when they want to. They have to have either a leak channel or some sort of gated channel. But sodium wants to come in because of diffusion. More concentration of sodium out here than there is in here. So if this active channel were always open, then you'd always kind of be away from negative 70 millivolts. So these channels stay open or closed. When it's time for us to get back down to a resting potential, that's when the potassium gated channels will open up. So when we're at resting potential, most of these gated channels are closed, both for potassium and for sodium. So we have 3 different classes of these gated channels, and these channels that are gated, just as you have a gate for a fence, they require a certain key to get into them, to open them up. First kind we'll talk about that you all are very familiar with are chemically gated channels. Chemically gated channels are going to require some chemical in order to open that channel up to let sodium come in. In the neuromuscular notes, we talked about how acetylcholine is a neurotransmitter that will bind to the receptors on the motor end plate and open the channel up to allow for sodium ions to come through there. So they open in presence of specific chemicals, for example, acetylcholine at the binding site. But there are various other neurotransmitters. There are about 90 neurotransmitters that we know of, and we'll talk about several of them in the next upcoming weeks. We find chemically gated channels on the neuron body, the cell body, and we also find them on the dendrites as well. Voltage-gated channels aren't going to respond to chemicals being released and binding on the motor end plate or binding onto the postsynaptic cell. Voltage-gated channels respond to changes in transmembrane potential. So if there is a change going from a negative number to a positive number, instead of being at negative 70, maybe we're at negative 65 or negative 55, that will trigger the channels in that area to open up, so, or to close. Have activation gates that open and inactivation gates that will close. These are characteristics of an excitable membrane. Places that we'd find these voltage-gated channels are in the axon of the neurons, the skeletal muscle sarcolemma or the plasma membrane, and cardiac muscle cells. And the third type of gated channel is a mechanically gated channel. These are going to respond to membrane distortion, and that distortion can be in the form of sound waves, like those that are used for hearing. It could be in the form of touch, pressure, vibration. Those things will actually distort the membrane itself and pull the gate open. So now that we've talked about how we maintain resting potential and the role of sodium and potassium, and you've established that they have pretty big roles in maintaining resting potential and the job of the sodium-potassium pump. We also talked about how sodium potassium can passively get across the membrane through leak channels, and then we even talked about how sodium potassium can actively move across the membrane through any of these various types of gates, whether they're mechanically gated, voltage gated, or chemically gated, which means chemically gated, they need a neurotransmitter to open or close that gate. Voltage gated, there needs to be a change in that transmembrane potential. We're just getting away from negative 70 millivolts and going positive. And then for mechanically gated gates, I guess we would say, mechanically gated channels. I could not think of that word. For mechanically gated channels, you'd have to have some sort of pressure or distortion to the membrane that opens it up. Now, once the channels are opened up, whether it's chemically, mechanically, or voltage-gated channels that are open up, whatever that stimulus is, because all of this stuff is, these are just different stimuli. Change of membrane potential to stimuli, membrane distortion, touch, pressure, vibration, acetylcholine. Those are all stimuli. So, and we just found a way to classify all those stimuli. So once any one of those stimuli opens up that channel, there will be an influx of sodium ions that come in. Those sodium ions, because those are typically the channels that are opened up by any of those stimuli. So the sodium ions, sometimes they're potassium, and we'll talk about that in a second, but when those channels are opened up, the sodium ions come in. So directly in that local area, we're going to go from a negative number to a positive number. At that point, when we have those positively charged sodium ions coming in, and we're going from this negative number to a positive number, we have generated what we call a graded potential. Because in that localized area, we've had a change in transmembrane potential. Now, this graded potential, it depends on how much sodium comes in there, that it's not going to be able to spread very far from that site of stimulation to where those channels were opened up. So that stimulus that opened that channel is going to produce a localized potential known as a graded potential. And that's why we said way back here, graded potentials may or may not produce an action potential because it has to be a pretty big change, a pretty big transmembrane potential change away from negative 70 millivolts in order for us to generate an action potential. But locally, just at this one area where you have those chemically, mechanically, or voltage-gated channels opened up by that stimulus, then it's going to generate a graded potential. So in that resting state, we have opening sodium channels. So we've had some change take place. We were at a resting state and we've had acetylcholine open up the sodium channels, or it was a change in membrane potential that opened it up, or it was a sound vibration that opened it up. But at any rate, some stimulus opened up the sodium channels and it produces graded potential. So that resting potential, that negative 70 millivolts, has been exposed to a chemical, to sodium. Sodium channels open, sodium ions enter the cell. Very important to understand. When we're getting away from negative 70 millivolts, when we're trying to develop an action potential, that's what AP stands for. When we're developing an action potential, we need sodium ions to come in. Now, doesn't this sound familiar? Remember when we talked about the neuromuscular junction, when we said that acetylcholine was released from the presynaptic cell and it would bind to the motor end plate of the muscle cell. The binding of acetylcholine to those receptors opened up sodium channels. Sodium was able to come inside the cell. This is the exact same thing as we talked about in the muscle notes at the neuromuscular junction. So when sodium ion comes in, we go up from negative 70 because we have these positively charged ions that are coming into the cell. That is what we call depolarization. Now, so far, we just said we generate an action potential. I just left it at that. Depolarization means that those poles, the negative inside of the cell and the positive outside of the cell, they're separate. They're no longer there. You've taken them away. If you declaw your cat, you took the claws away from them. If you dethrone a monarchy, that means that you've taken the throne away from them. So D means to take away. So with depolarization, poles mean that there's going to be opposites of them. So you have the north and the south pole. If we take away the positive and the negative aspect of this, then it's what we said to be depolarized. Because now, when depolarization takes place, we're not going to be at a negative number. In fact, we're going to go up and be positive. So it won't be that the outside of the cell is more positive than the inside. It will be that they're both positive together for a while. So that is what depolarization is. And we've just been using the term action potential so far. So depolarization, the way we defined it, is a shift in transmembrane potential towards 0 millivolts. So we're getting away from negative 70 millivolts. Well, Kelly, how do you do that? Well, we have to have something that opens up those sodium channels to allow sodium ions to come in. Well, Kelly, what is that something? Well, it could be a vibration, and we'd call that a mechanically gated channel. Well, it could be a neurotransmitter. We call that a chemically gated channel. It could be the fact that a portion of the cell right next door changed its membrane potential. So we were able to change us because we're right next door to it. So that's a voltage-gated channel. So at any rate, some stimulus came along and opened up those sodium channels. When sodium comes through, it produces this local current, and we call that local current, or that local change in transmembrane potential, a graded potential. So it depolarizes the nearby membrane. Graded potential. Remember, graded potentials don't spread out very far. Then this change in potential, very important to remember, that's why I have an asterisk by it, the change in potential is proportional to its stimulus. So if we only have one sodium gated channel open because only one acetylcholine bound to the receptor on the motor end plate, then, well, it's not going to give us a huge change in potential. So at this point here, this is where we once again get to a graded potential may or may not cause an action potential, because if that stimulus is not large enough, you won't have a change in negative 70 millivolts big enough to affect the entire length of the axon or to affect the entire cell. However, if you do depolarize far enough, if that change is big enough, then it will generate an action potential. And once an action potential happens, it's gone. It's either all or nothing. So after we have depolarized, and I'm going to start drawing this graph here, and you guys are going to get used to seeing it a lot, at negative 70 millivolts, and then we'll get plus 30 up here. And that's resting potential. At this point, we have depolarized. Now that we come down, we are repolarizing. So this side, depolarizing, and we've already discussed that sodium ions are coming in. And they're going into the cell. Now at repolarization, and I'll just write RP here, that means the stimulus is removed. The acetylcholine is removed by acetylcholinesterase, like we talked about in the neuromuscular the neuromuscular system chapter, or the sound waves are no longer there. So that mechanically gated channel, that membrane is no longer destroyed, it closes it shut. Or the voltage change is no longer there. Whatever it is, the stimulus is removed. So the transmembrane potential is now going down. So it goes and rests in normal. At this point, you have potassium channels open up, and it's going to kick potassium out. So to depolarize, sodium channels open up, and we bring sodium ions in. So we bring so many sodium ions in that we get to be positive, and we have depolarized, which created an action potential. What goes up must come down. So in repolarization, we close those sodium channels so no more sodium ions can get in. And because we're so positively charged, we got to kick out some of those positive guys in there, and we're going to kick out potassium this time. So potassium gets kicked out in repolarization. We'll kick out so much potassium on here that we end up, and that's potassium out. We end up kicking out so much that we actually overshoot our mark and get down to negative 90 millivolts. So positive ions move out, not into the cell, and we get really, really negative. And that's what this says. We get super, super negative here. How negative do we get? Well, we get so negative that we get down to negative 90 millivolts, which means we overshot our mark of negative 70 millivolts by a little bit here, by about 20 millivolts. We've overshot our mark. And this is where we'll have to have the sodium-potassium pump come back in to reestablish us back at negative 70 millivolts, where for 3 sodium ions we kick out, we bring back in 2 more potassium ions. So the effects of a graded potential, and we'll talk about all that stuff in that graph again. The effects of a graded potential, they're going to depend on, it happens at the dendrites or in the cell bodies, and they trigger specific cell functions. We also have graded potentials that happen on the motor end plate, and that's that point there. That's where we have acetylcholine that is released and binds to the receptors in the motor end plate and allows for sodium ions to come in and generates an action potential within the cell. And there should be enough acetylcholine that binds to those receptors that it allows for enough of these sodium ion channels to be open to bring enough sodium ions into the cell to generate an action potential. So here we're looking at this whole shebang on what's happening in your cell. So we're resting, negative 70 millivolts. These purple balls are going to represent sodium. These are sodium channels. And of course, we're negative on the inside, and we know that because our electrode tells us we're at negative 70 millivolts. This is going to be, what kind of channel do you think? Since we have these little balls that are just bound to those receptors there, so they were closed. But then when the balls bound to those receptors, they were open. So do you think this is a voltage-gated channel, a chemically gated channel, or a mechanically gated channel? What openness? Yes, awesome. Chemically gated channel, absolutely right. So when the balls weren't there, they were closed. So this stimulus, this chemical, and we're just going to call it acetylcholine because we're familiar with that. So this chemical opened it up. As it opened it up, we have these sodium ions coming into the cell. So now we've gone away from negative 70 millivolts, where we're a little bit more positive, and negative 65 millivolts. So as we continue to allow more sodium ions in there, we're going to get a little bit higher. We're going to go from negative 70 to negative 65. Notice there are no channels here open yet, so no sodium ions coming in. We're getting more positive. We're getting further and further away from negative 70, so there is a good shot that there's greater potential. This localized change in transmembrane potential can become an action potential. So this is really just discussing what we saw on those other slides, so I won't spend a whole lot of time on it. But the greater potential depolarizes at the very beginning of the axon, and we call that the axon hillock, and it needs to be at least 10 to 15 millivolts away from negative 70. So once we get about 10 to 15 millivolts away from negative 70, so at negative 65 or negative 55, then we say that we have reached threshold. Once we've reached threshold, that's kind of like squeezing the trigger on a gun. It's going to completely just take off. It's going to go all the way. We're going to generate an action potential. And your book used to give a really good example of no matter how much pressure you put on the trigger of a gun, if you put enough pressure on it to reach its threshold, that bullet's going to come out with the same velocity. So whether you squeezed it really hard, like, oh, Jody, my office mate, she's sleeping with my husband, you bitch, and I shoot her very aggressively, or if I'm just like, I don't know if I like to, but I feel like I need to shoot her and I just squeeze it a little bit. That's not going to be a good defense in court. Well, I didn't squeeze the trigger that hard, so the bullet shouldn't have come out that fast. It doesn't really work. Same thing with your action potentials. Once you're ready for it to go, once you've reached threshold, it's out the gates. So if you get to that point where we're at negative 60 or negative 55, we are going to generate an action potential. Very important to remember that once we reach threshold, that action potential either happens or it doesn't. So we get to threshold, it happens. If we don't get here, then it's not going to happen. And that's what we call the all or none principle. Action potential is either triggered or it's not. If the stimulus exceeds the threshold amount, if we get to negative 60, negative 55, that action potential is going to be the same. Just like squeezing the trigger on that gun, whether you squeeze it very aggressively or if you were to squeeze it just very gently, like, I don't think I want to do it, that bullet's going to come out the same velocity. Same thing with your action potential. It's going to come out at the same velocity. It's going to either be triggered or it's not going to be triggered. So we already talked about step 1. We depolarized to threshold, negative 60, negative 65. Step 2, those sodium channels are going to have more sodium ions rush into the cell. We call that rapid depolarization. The inside of that membrane goes more from a negative number to a positive, so that's why it's depolarization. It's no longer negative on the inside and positive on the outside. It's now going to both be positive. So we have reaching our threshold here. Once we've reached threshold, we have an influx of these sodium ions that are coming in. Notice for our potassium, those are going to be our orange balls. Those potassium channels are closed. So we have sodium ions that are coming in, they're coming in, they're coming in. And now we've not only gone from negative number, we're at a positive number. And we are going to have all of that happening until we reach about plus 30 millivolts. Once we get to plus 30 millivolts, a couple of things are going to happen. Potassium channels are going to become inactivated. Sodium channels become inactivated, and potassium channels are going to become activated. So we're going to close the sodium channels. We don't want any more sodium coming in because we want to repolarize. We want to come back down. But in order to do that, we got to kick out some potassium. So potassium channels open up, repolarization begins. Sodium channels, we're done with sodium. We're going to close them. So now, notice the purple for sodium. Those are closed at plus 30 millivolts. And we're going to have the potassium channels open up, and they're going to leak on the outside of the cell. And we're going to just kick out potassium, and we're going to end up kicking out so much potassium that we get really, really low. In fact, the potassium channels start to close when we get to negative 70 millivolts, but they don't all close at the same time. So because they don't all close at the same time, we end up becoming hyperpolarized, which means that we end up pushing out a little bit too much of the potassium ions. So because of that, we need the activity of the sodium-potassium pump to bring in some of those potassium that we kicked out and get us back up to negative 70 millivolts. So if I draw this graph for us again, I'm going to give it a separate page. Oh, that's not what I'm going to do. So if I were to draw this graph again, here's at -70, here's at +30, and you all should be very familiar with this graph, and you should be able to replicate this graph. So let's put this -70 a little lower. So we're at -70, we generate an action potential, sodium ion channels open up, sodium ions come in, we get to +30, we need to repolarize, sodium ion channels close, potassium ion channels open up, kick out potassium, kick out potassium, kick out potassium. At this point, at -70 millivolts, we're going to close those channels that have been kicking out potassium, but we're not going to be able to close them all at the same time. So what happens is that we overshoot our mark a little bit. And by overshooting our mark, we call that hyperpolarization. But to get us back up to -70 millivolts, we're going to have the sodium-potassium pump bring us back up to this level. So here, we depolarized. Here, we repolarized. Down here, we called hyperpolarization. What got us back up to -70 was the sodium-potassium pump. So then we have our hyperpolarization here. We just left out too many of those sodium ions, so there's too many of them that are leaking out there. All of these channels should be closing pretty soon, and then we'll have the sodium-potassium pump that will bring us back up to where we need to be. So because there are some timing issues here, it doesn't all happen just like, they happen really quickly, but there are some timing things that we have to deal with. We have to talk about refractory period. The refractory period is the time from the beginning of the action potential to when we go back to our resting state of -70 millivolts. During this refractory period, the membrane's not going to respond the way it normally would to any stimuli. And there are two aspects of your refractory period. Absolute refractory, when there absolutely is no action potential that's possible. Why? Because we already have sodium channels that are opened up and activated. We're already generating an action potential. They're not closed yet. We're already at a positive number, or positive enough that there's no place further positive to go, because once we get to +30, those channels are going to be closed up for sodium. And then you have your relative refractory period, where this is where we can have another action potential, but it's relative to the size of the stimulus. It's all relative. So if you have a very large stimulus, then it can initiate an action potential. During relative refractory period, many of those sodium ion channels are closed. So our membrane potential is almost at -70 millivolts. It's getting pretty close to normal. So if we have a big enough stimuli, enough sound, enough pressure, enough whatever it is, then you'll be able to, you may be able to generate a relative refractory period. Or I'm sorry, an action potential. So the sodium-potassium exchange pump, remember, it maintains our -70 millivolts. It requires 1 ATP to bring in 2 potassium for every 3 sodium it kicks out. If you don't have any ATP to power the sodium-potassium pump, the neuron's going to stop functioning. Why is the neuron going to stop functioning? We're going to keep losing out those sodium ions. They're going to keep leaking out of the cell. And as a result, we'll get from -90 to -100 to -120, where no matter how big the stimulus is, it's not going to be enough to get us up to +30. We'll just be so negative that there will be an action potential big enough to get us back to where we need to be. So in order to get this pump to work, we need energy. Without energy, then the pump doesn't work. The pump doesn't work, we get super negative. We get super negative, we can't generate an action potential. Can't generate an action potential, neurons stop functioning. So another very important use of ATP. We talked about in the muscle chapter how we needed ATP to recock the myosin head. If it didn't do that, then you couldn't get subsequent contractions. So here's a much prettier graph of what I tried to draw. We have our resting potential, we have our threshold that we've reached here, active depolarization, and in depolarization, what channels are open, sodium or potassium channels? Sodium channels open up, and we go from a negative number to a positive number. In repolarization, what channels are opened up this time? What channels open up in repolarization? Sodium or potassium? And you can just write Na or K. Absolutely right, potassium channels. What about the sodium channels? Are they still open at this point? No, sodium channels are not open at this point. So we kick out potassium, kick out potassium, kick out potassium, kick out potassium, start to close them now, but they don't all close at the same time. So we kick out a little bit too much potassium, and then the sodium-potassium pump helps to bring us back up to -70. So notice in this portion here, from the time we reach threshold to the time when we're just about at the end of repolarization, we're at about -40 millivolts, we are considered in absolute refractory. That means during this time period, you cannot generate another action potential because, well, sodium channels are already opened up here. However, in relative refractory, if we have a big enough stimulus, from the time we get from about -40 on down, if the stimulus is big enough, then we can generate another action potential. So it's relative. In absolute refractory, we absolutely cannot generate another action potential. So absolute refractory absolutely cannot generate another action potential. In relative refractory, it's relative. So we can generate one. It's relative to the size of the stimulus here. With cardiac muscle cells, remember we talked about cardiac muscle and the role of calcium, that we don't have a sarcoplasmic reticulum that stores calcium? Well, for cardiac muscle cells, they have a longer absolute refractory period. So there's a longer period in time. In fact, their graphs, instead of looking like this, they kind of look something like this. So that during this period here, from here to about here, they can't have any action potential that takes place. It has a very long relative or absolute refractory period. And it allows, the cardiac muscle does this to try to keep the heart muscle beating succinctly. So kind of file that in the back of your mind because we'll talk about that again in A&P2. So propagation of the action potential is the movement of the action potential along the axon. And it starts in the axon hillock, which is the beginning of it. And this page might not be the same, but like page 396, I believe that says. But it moves, starts in the axon hillock. That's where the gradient potential started. And it kind of moves along the length of the axon. And it's a series of these repeated actions. So we have this portion of the membrane becomes depolarized, and then the next portion becomes depolarized, and the next portion, and so forth. The parts along the axon where it becomes depolarized, they're usually voltage-gated channels that open up in response to the change in the change in membrane potential from the neighboring part of the axon. There are two ways that we can move this potential. What we call continuous, that means it just moves along every single part of the axon without stopping. And those happen on axons that don't have any restriction or myelination. And then you have what we call saltatory propagation. And they're unmyelinated axons. And saltatory propagation, they're going to, the action potential jumps from one node to the next. Between the two, saltatory propagation, where they're on myelinated axon, takes place faster because it has fewer stops to make because it jumps from one node to the next. Whereas with continuous propagation, every single portion of the axolema, the plasma membrane along the axon, has to be depolarized, whereas in the saltatory propagation, only certain spots able to jump. So instead of it being 50 spots for continuous propagation, it might only be 5. So the action potential takes place faster on myelinated axons because that myelination restricts the movement of that charge, and it can't go through there. The potential, the electrical activity can't go through there, so it has to jump over it. So in continuous propagation, one of the axons done along an unmyelinated axon, it affects one segment at a time. All of these steps are the exact same as we talked about before with generating an action potential. And big take-home message is that notice it's got to move across every single portion of the axon. So it's got to continuously move across there. So we had it start here, and then we're going to move it on this way, and so forth. Or actually starts here and move it on this way. So every part of the axon has to be stimulated. So the first segment reaches the refractory period, and then localizes the next, and the action potential. The cycle repeats itself until it gets to the end. Now, with solitary propagation, this is where the action potential moves along a myelinated axon. It's faster, uses less energy, and it jumps from one node to the next. So that depolarization is only going to happen at the nodes or the portions of the axon where there is no myelination. All right, so that is all we're going to discuss today. On Thursday, we'll talk about axon diameter effects on speed and synapses, and we'll also talk about some neurotransmitters. And Thursday, we'll have a good chunk of this done, and we should be finished with all of this by next Monday. So next Monday on the 26th, let me look at my calendar and make sure that's right. Yes, so next Monday on the 26th, we will have a quiz, and it will cover chapters 10 and whatever we finish covering for chapter 12. So all the muscle notes will be on there, and everything up to probably, let's see here. So let's see, I'm trying to see where we'll probably end to this page. So up to information processing. So your quiz will cover everything up to here, because this is where we'll end up stopping. So that's about 79, so like 30 slides extra. So everything from the the muscle chapters, all of chapter 10, and everything up to this portion of our notes are potential things to be on your quiz. Things that I would especially pay attention to were events at the neuromuscular junction, understanding what happens, knowing how a muscle contraction takes place, knowing the parts of a nerve cell, knowing what an action potential is, depolarization, repolarization, the role of sodium, the role of potassium. All of those things are very important and stuff that will definitely be on your quiz. So there's a lot of material that could possibly be covered, because I want to start preparing you for your test, because the week after our quiz, we will have our second exam, which will cover all the muscle notes, all the nerve notes. Only 2 chapters, but they're 2 pretty big chapters. So the quiz will still only be 15 questions, multiple choice, but the topics that they cover are going to be varied between chapter 10 and chapter 12. All right, so I will see you all soon. Have a great day.